Now, the next invite talk is Professor Rajen Kumar Sinha. Now I request my student Pranav to speak about Professor Sinha. It's over to Pranav.
Thank you, sir. It's a proud privilege on my part to introduce Professor Rajen Kumar Sinha, sir. Professor Rajen Sinha has completed his post-graduation from Utkal University, Bhubaneswar, Odisha. He has obtained his PhD from Indian
Yeah. Unless you confirm it, I cannot start. Okay. So, good morning, everybody. And at the outset, I'd like to thank Dr. Sudhakar for the invitations. And also I'd like to thank my friend who is the present director of OMS, that IMA, for the invitation. And actually, in that when it was initially decided to have an OMS, he just talked over phone, and then he wanted to have the OMS. I was a bit excited. Okay, because I will have an opportunity to visit my home as well if I have a conference over there in Bhubaneswar. So, and then due to some unfortunate things, it has been moved to online mode. And after that, I think when Dr. Sudhakar communicated that, this conference is as per the schedule. So I'm extremely happy, and also thank this Sudhakar and his team for organizing this event at the difficult times. Well, coming to the point, the title which I'm going to talk about is basically on the composite finite element method for the parabolic problem in non-convex polygonal domain. And this work I have been doing for the last few years, the recent past, and this work I have done with one of my student, Dr. Pramanick. Presently he is an assistant professor at the NIT Calicut. So my overview of the presentation is as follows. So I'll just introduce the model equation that which I have considered. So basically, we have considered the heat equation, and give you some word about the motivational word regarding why this FEM, why is this composite finite element, and how it is going to be useful while dealing with this non-convex domain. And then I'll talk about who is very important. That is your composite finite element discretizations. That is basically where which is the important part of this construction of this composite finite element spaces. And then we'll talk about the error analysis, because this is the when you do the any numerical analysis of any kind of PD, so we need to involve, if you wanted to do some kind of any new methods, you need to justify that how good your method is. That is only through this convergence analysis. And I will present some numerical result as well to show this efficiency of this method. And I'll talk about this, some concluding remarks and from future avenue in these directions. X and t, and u denotes basically the partial derivative of with respect to time. Okay, and this is the Laplacian of u, and initial conditions u at t equal to 0 is given to be u naught x. So here you represent the temperature distributions in this domain. Okay, so basically when I talk about this non-convex domain, so I just look at this kind of the domain which I have just put up in the screen. So what is the difficulties with this? This is first one is a L-shaped domain. As you can see that you have a corner over here, okay, and this is an H-shaped domain, okay, with introducing more complexity to the domain, okay, to the problem. And the third one you can see it is an square-shaped domain with a finger-like course from the both end. Okay, so this type also domain that you can see while designing the chip design and so forth. Okay, so respect this method, right? So if you look back, so in earlier during 60s, the finite difference method was introduced to basically to deal with this or to find the numerical solution to differential equations. As all of you know that this method is only best suited for a square domain. And when you try to deal with the curve boundaries or complicated domain, then several technical tricks you want to employ to overcome this problem. And another is that, and that convergent analysis is hard to prove, right? And as you know, FDM requires that your solutions require to be smooth because it relies on the Taylor series expansions. Okay. So, with the introduction of this FEM, it greatly solves this problem that simplifies the problem of finite difference method. So it is still now it is a very powerful trick that people are using. This method is used by the scientific community. Okay, because it has a strong mathematical foundations where you can do the error analysis and where you can determine these a priori bounds. So before you go to the computations, you know a priori that if I do this computation, I am expecting this or the numerical that numbers which you are going to generate on the computer, you can give a meaning to those numbers, and you can tell that yes, I can able to accept those number or not. Okay, and further you see this this FEM also can be used that for the adaptive refinement strategy for if you have a singular kind domain. But those adaptive strategy, because it rely on the a posteriori error estimate. Okay, so I'll maybe talk at the end regarding this. But what is the difficulties in this FEM is that if your domain is convex, okay, then FEM, what it requires that you require finer mesh to resolve the boundary. Okay, so what it does, because if suppose you have a boundary condition is given, suppose you have a Dirichlet boundary condition is given, then your finite mesh is required to be small enough to resolve this boundary. So what happened in this process, as a result, it increases the dimension of the finite element space. Okay, and in particularly when you have the problem non-convex domain, the domain which I have just shown in the screen, so you require your degrees of freedom in finite element method is going to be very high, right? And it is computationally it will cost, it is not numerically efficient, okay, to deal with this non-convex type of domain. So let me give you what happens in the we do in the FEM, the finite element method. So what happens, you have the abstract problem, okay, so you need to find a solution in some infinite so vector space, okay, such that your U satisfies this operator equation, say LU equal to F. F is some general operator, okay. So this is basically I'm giving you the general overview what it happens in a finite element. Then you construct a finite element subspace of this V, okay, and then look for an approximate solution UH in this VH, okay. Of course, the dimension is finite, such that LHU equal to UH equal to F of H. That means you discretize your continuous problem having infinite degree of freedom, and you discretize and to obtain a discrete problem having a finite degree of freedom, right? That's the whole idea behind of the numerical analysis. And then when you have it, then you need to investigate what are the errors involved in this process, right? So the error involved in this process, basically we use a priori error estimate to determine this error, right? So if U is the exact solution and UH is your finite element solution, then the error basically it is bounded by some constant which depends upon so regulated the solution as well as multiplied by a factor h. Here h is basically your discretization parameter, and m refers to basically is the order of the accuracy. Okay. So this is what I said before, that this FEM has a the advantage that before you would go to the computations, you know the at least suppose you use the piecewise linear element, so one can expect that you can get order of h square in, suppose in L2 norm. If you use some gradient norm, then you can get order of h, right? So this is the basic idea of this FEM. And look at this some results associated with this the elliptic boundary problem. So I'll just give here before, because to some distributions. Okay. And this space is basically, it consists of all functions in L2, so their first order derivatives also is in L2. Okay. In the sense of distribution, and the functions, the vanishes on the boundary. Of course, it is in the sense of trace. So I'm not going to detail on the technicality of this. So now this, what the importance of this convex domain is that if f is in L2, your u is in this space S2 regular. Okay. And if you take the piecewise, if you use the piecewise finite element, piecewise polynomial to approximate your solution, then one can expect in that error in the gradient, which is of order h, and in the L2 norm, you can get order of h square. Okay. And this error analysis also, it reflects that you require u to be in H2 regularity on u, right? But now if you look at the non-convex domain, because of this kernel, you have the several kernel. So if omega is non-convex and if half f is in L2, then you doesn't possess this H2 regularity, right? That means you will have u is going to be in h of 1 plus s. This basically, it's a fractional order Sobolev space where s lies between this. Okay. And u satisfies these regularity estimates. Now the question is this: if since u has a less regularity, now you do analysis of this convex domain is not going to work, because of this regularity result is one of the play important role in the convergence analysis, right? So for the non-convex domain, what happened that because of this modified that you have this regularity, one can expect your convex order is going to be less in compared to the in case of convex domain, right? That you can see from here. Well, so these are some observations that you can see in the FEM for the convex domain and as well as the non-convex domain. So then natural question is that why this basically is composite finite element? As I said already before, that in FEM, one is required to this finite element mesh has to resolve the boundary to get a better convergence, right? On which in fact it increases your number of degrees of freedom. Okay. So as a result, your dimension of the space is going to be very large. Okay. And if you have a domain is very complicated, then you can expect that the dimension is too huge and the computational cost is going to be high, right? So what this composite FEM it does, the composite FEM basically, it is a composition of the two that here you have used basically two scale discretizations for the in order to construct this composite finite element space. So one is basically we have the coarse scales. So there are two scale introduced. One is coarse scale, another is fine scale, right? The coarse scale, it describes these solutions in the interior domain at a proper distance from the boundary. I'll just come to I'll show you the domain, the discretization of this. I just wanted to just give you what are the basics idea of this CFE, that discretizations. So you need to introduce two scale. One is basically responsible for the discretization, the interior of the domain. Another is basically at the near the boundary to resolve this the Dirichlet boundary conditions. Okay. So what happened in this case, the degree of freedom of the CAP, they are only located at the interior nodes at a proper distance from the boundary. So as a result, what happened? Your finite answers, your dimension of the space is going to be very less. Okay, and the computational cost they become very less when you compare to the finite element method. So here I'll just give you the see if the discretizations. Here is a convex domain. So you have introduced this coarse scale. So this is the coarse scale discretizations, and here is the use the smallest that small s to discretize the fine scale to resolve this boundary. Okay, and these are the some HK is the diameter of this the triangle in the interior region, that shaded region, and your h is the maximum of this the diameter, the maximum of this HK. Okay, that you can take the longest edges of this the triangle, and the near boundary triangle, it satisfies some the distance from the triangle, the nearest triangle from the boundary, it satisfies this inequality, because here see the this parameter sigma distance, it controls basically the width of this the neighborhood of this the distance that from the boundary. So, and here tau s is basically is the fine scale grid, which we call it it contains the slave nodes. Okay, so these are here, these are the degree of freedom where your finite element the spaces basically depend upon this degree of freedom. Okay, and these are the nodes that is near to the boundary, they are called the slave nodes. Okay, here basically here is the discretization for the non-convex domain, as you can see. Okay, which is our the subject of the interest. So all the two scale grid we denote as a tau h, which basically it consists of two scale discretizations, and the sons of k means it consists of all triangle in this, that the tau contained in the triangle k. Okay, and the minimum of this we call this we call as a small h. Okay, so the basically the CAP discretizations, the basic idea is that the finite element space which you construct is going to depend upon only these degrees of freedom here. Okay, instead of what happened in FEM, that in order to resolve this boundary, one has to refine the mesh near the boundary. So as a result, your dimension degrees of freedom is going to be huge. Okay, so here the introduction of this the small scale to resolve this boundary, and this boundary condition is cleverly transformed into the basis function of this finite element space. Okay. So here this the stopping rate for defining this the finer scale grid, as I said, the nearby boundary triangle, this satisfies this conditions. This basically give you your stopping criteria to the algorithm which will take care of this refinement procedure near the boundary. And for a slave node, this is the collection of the slave node, as I said, the slave nodes, that is the nodes that are around the boundary. It determines for every slave nodes in the interior mesh, and such that the closest points, the examma on the boundary, it satisfies this one. Okay, the distance from the slave node, okay, to the closest triangle, it satisfies this. Here, this is the control parameter. Okay. So these are you can see there are two pictures here. The slave node for each, the slave node X, the choice of the closest, the simplexes here in the case of convex domain, convex domain, or here in the case of non-convex domain. So these are the basically, as I said, your CFE discretizations. First, you have to introduce the two-scale grid for the refinement of the grid. Then you specify the various, identify the degree of freedom. So these are basically the of this freedom of basically the number of the nodes associated with the slaves, the finer mesh. Okay, and because since your safe functions are defining your finite element basis functions is defined over the your interior grid point. So how do you assign those? Those are the point. To assign the finite element value, finite element functions that to take the value at the safe functions or at the finer nodes. So it is done by the extrapolation operator. So this extrapolation operator, what it does, so it via the grid functions, it defines we define an extrapolation operator. What it does that when x is the interior, so it agrees with this the value of the function at the nodal point. Okay, so if x is the slave node, right, then the value of this the functions become the difference between this is the nearest triangle to the slave node and the value of the point that is lies on the boundary. Okay, so otherwise it is 0. Now if you observe that if you is with this v tilde x for x in the point, then this will be this value of the function at this is will take the value of the phi tilde at the grid point. This is in the if it is a slave node already defined in the previous in the here as is defined. If it is a slave node, if it is in the boundary, then we will have this. Okay, or it is the slave node, one of the slave node. So once you have the construction of a composite finite element space, then you can one can go for a finite composite finite approximations. But before prior to that, some of the development in this area, I just wanted to give some the credit to this authors. You know, he's a well-known numerical analyst. So Hugbus and Chowter, they have actually introduced this composite finite element for the elliptic problems. Way back in 1997. Okay. While they're dealing with this Neumann type of elliptic boundary problem, and later they extend to the deal with this Dirichlet boundary conditions and introducing the adaptivity for generating this your slave nodes. Okay, and later on this Rake et al. They have extension their work to for the complicated the domain with complicated geometry. And this one case they extend their work for the Stokes problem over the complicated domain, and later these two authors they have extended work for the parabolic interface problem, because the interface problem you have because this the CFE is very well you can resolve your interface. So now once you have your composite finite space, so you can pose your problem to the finite element setting. Here is the basically as a standard practice, you can weak formulate the given problem. Okay, so one has to find a solution in this space which satisfies this. So this is the standard the weak formulations, and then you pose the problem in a finite setting. That here you look for a composite finite solution in this composite finite space which satisfies this. And the existence of this is one can prove it though exactly the proceeding in the way that is done for the heat equations. Okay. Well, let me just uh, just please I request the organizer to remind me if I have crossed time, because I do not want to rush up, because I try to speak slowly whatever possible way. So what exactly, let me give you, because there are many new participants that are new to this maybe area. So for them, let me just give you one brief idea that when you try to do the convergence analysis in finite element, what happened from this, that the direct comparison between you and the finite element solution, it doesn't give the optimal order convergence. He has introduced a concept called the elliptic that projection, or called the these projections, where they projected the elliptic pattern to finite dimensional space and introduced this elliptic process as a intermediate object. They split the error and try to determine the solutions. Okay, and to recover this optimal order convergence. So when I say optimal convergence, that optimality in this sense that one would expect that when you employ these approximation properties, because when you do the finite dimensional approximation, you have the approximation property, a standard approximation property. So in that sense, we call it is an optimal error estimates. Okay. So what you do, you decompose the error. Okay, you introduce this the elliptic projection in the case of standard finite element. The idea we simply borrow the same idea from there and try to see how it behaves in the composite element here, because here we have introduced two scale, and it is not so straightforward. I just wanted to tell you that is not so straightforward to deal with the analysis that has been done by the introduction of the Wheeler projection, because their domain is convex and so many more things was there, so it is easy to handle there. So because you have the non-convex domain, so and the solution do not have that much regularity, the required regularity. You have the less regular here. So but the trick that we have borrowed, we have used the same trick, because it is because direct comparison between the CFE solution U and has the lead to the same problem. So introducing this, then we thought of that. Let's see that we try and let us see whether we could able to improve that optimal convergence. Yes, so we did that way, and we try to split the error. We call this is to be theta. As you can see, this is the term which is sitting inside the finite dimensional space, and this is basically your called the parabolic type of error. Okay, roti. So sorry, this is your the basically the projection that error. That is when you use the elliptic projection. So that is the projection error. This is basically the parabolic type error. Now what we do, we try to get the estimate for this roti. So under these conditions, these two discretization CFP discretizations. So under this condition, so we have proved this error in the projections, that is error in the roti, that is uh, which is of order, as you can see, s to the power s log factor is there. Okay. So we prove this error estimate, it is optimal up to a logarithmic factor. Okay. And as you see, as expected, we have using the regularity as per the when your domain is convex, you do not have a regularity. So we know the regularity used in H1 process. Similarly, for the L2 now, so we have s to the 2s and log h. Now here I just want to remark that if your h, a small h, is of order h, that means when you have a single scale discretizations, that in case of finite element discretizations, you can see this is going to be order 1 log 1 0. So basically you will get you can recover the errors that you expect in finite element analysis. So that's the beauty. That's what means when you bring down to your one scale discretizations, you recover your results that you are already established in the finite element analysis. Okay. So we require not only this the temporal derivative also we estimate the error. So this plays a crucial result. So because to this error plays a crucial role in to obtain the error in because to obtain the to bound this error basically you need to bound this two term, right? So once you have a bound for this, so you need to bound this theta terms. So theta terms, if we have expressed that we can able to bound this theta in terms of rho. Once in the estimate of rho is available, so it's possible one can estimate the also theta as well. So combining these two elements of this detailed technicality, I do not want to just invite here. So of course, so the finally this error estimate in this partially discrete scheme with the special, so you can see the in the L2 error. So we have obtained this optimal error estimate up to a logarithm factor. Okay. And for the gradient, we have this sort of convergence. So these are the results that we have proved for the time dependent problem. Basically, we have extend this the class of the analysis of the stationary problem to a time dependent problem, because those the extensions are not straightforward that one has to do many things because well, so these are the some new the results that in this direction of your this composite finite element, and that was a long gap since the introduction of the composite elliptic problem to the time dependent problem. That is a huge gap, and that I think many students that you could able to get some results in the direction of the composite finite element. So now for the we have used the backward element time steps for the fully discretizations, because you need to do the fully to discrete in the time direction as well. And for that we have used type steps. We have this the convergent result. Okay. And as you can see here, as as expected, we can get a first order convergence in the time directions, which is the parameter discreteness parameter with respect to your the t directions, right? So similarly for the various time steps, as you can see, we also get the since you are using the backward steps, we get optimal order in time of your non-convex in the spatial region. So it is natural, you can see that is the analysis, it is reflected over here. Okay. And also we have some results for the non-smooth data, because when your data is simply an L2 functions, the previous case we have assumed the data to be smooth, but we have also extend the result when your data is non-smooth, right? So because when your data simply belongs to an L2 function. So in that case, you can see the one you can as you move away from the singularity, as you move away from the t equal to 0. So this result is basically you can see for data is in non-smooth data. Okay. So as I said, when you take a one scale discretizations, that our with smooth non-smooth initial data. So similar results also we have proved for the fully discrete case with non-smooth initial data. Here you can see that the data is non-smooth. first I've considered the smooth data case, and then I have also one case with non-smooth data cases. So here the domain, as I said, we have considered this as a square domain with a tiny finger-like coarse that has been removed from the board. Okay, and the coarse mesh that mesh size we have taken this, and the finer mesh this is to be taken this, and this domain. Okay, and you see these are the for various see that your the composite error that is reducing, right? It is the L2 error. This is going to be the H1 error. So okay, both as you can see they are decreasing. And then if you further reduce the your coarse sizes and try to observe the error, and then you can see that error is reducing, and also we have obtained this order of convergence. As you can see, the order of convergence that here you obtain that in case of that the CFE, it is almost optimal. Okay, and for this is for the H1 for the gradient norm, so we get which is of order, which is almost optimal. And this here the degree of freedom is this. So of course, if one to compare, unfortunately I do not have it, but you can one can I have the results one with my students. There's a paper I should show you, and at that you can see those. So here I've taken a non-smooth data. Look at here. Here the earlier case example is smooth data. Here I have to consider the non-smooth data in the domain, and the domain I have considered to be a S-shape domain, which I have shown in the beginning, and the various values of H are shown here. And this type of domain that we have considered. And you can see for various step size, as your the inner mesh we decrease the mesh size, your results as you can see it's decreasing. And you can in the CFL2 error estimates for non-smooth data we have obtained the L2 error estimate, which is of course C. So because of this non-smooth data, so our this result is which is the logarithmic factor that is reflected in the this order of convergence. Okay, so this is your composite solution, the plot of composite solutions. Okay, okay, I just wanted to conclude with this final word. So what I just wanted to convey is that so the trick that this composite finite element that we have seen to find works well when the domain is very composite Fallon discretization. It deals with this kind of domain very nicely. And further, you can see still now we do not know how to extend this composite for the domain in R3. Okay, this because we do not know how to handle this the shape node at the at R3. So still this result is quite wide open till now. And further, this method that CFE that was we have developed, one can apply to a class of time dependent problem to a complicated geometry. Okay, and further one can also come up with this adaptivity of this composite finite element. So far we have only obtained this a priori error estimate. The a posteriori estimate, this type of problem still wide open. And then as I said, this adaptive procedure for this composite finite element also wide open. So what happened in a posteriori estimate, because in a priori estimate you cannot quantify the error because your error estimates depending upon your exact solution of the U. But when you do not, because when you have a complicated domain, you do not know the U, right? So in that case, what happened? The a posteriori estimate where your estimator will depend upon your computed solutions, and you can using the computed solution you can refine the mesh accordingly. So it's very interesting, but it's a challenging one. Still it is wide open. Okay, these are the very nice books. So as well as for the to exploring to the basically non-convex domain analysis. So one of these are the author which they have dealt with this parabolic equation in the non-convex domain. And this is the book which one can see the how to deal with this non-smooth domain, elliptic problem in non-smooth domain by the Griva. It's a very good book, and these two books, and also the singularities in the boundary value problems. So these books are quite those who are interested, I suggest them to can go through it. It's a very nice book. And these are the authors that have dealt with this elliptic composite finite element method. Later on, as I said, my student and myself, they have done this composite element to the parabolic problem for smooth as well as non-smooth domain with a both for smooth as well as non-smooth initial data. That these are the works that we have done. So that is that the work which I'm presenting it that you can see in this is the very recent article. Okay, that I do not want to already have taken little more than my that is specified to me. I apologize for this, and I thank you for your attention. If any questions, why you happy.
Thank you, sir. Now I invite the audience to ask some questions. Okay, for accepted. Thank you, sir, for delivering such a good lecture. I thank to you on behalf of our organizing committee and on behalf of me. Thank you, sir. Now,
Thank you. Thank you very much.